Could we have slides, please? Great, thanks. Good afternoon, everyone. Before I start, I'd like to acknowledge some of the co-investigators, co-authors on this presentation. Gail Paulson from Honeybee, Julie Kleinhans from NASA Glenn, Jim Smith, John Trotwain, Jackie Quinn from NASA Kennedy. There is going to be on this coming Friday, there's going to be an entire session on resource prospecting mission. But I put this slide just to recap what the mission or resource prospecting is all about. The goal is in situ resource demonstration, prospecting for volatiles, extraction of oxygen from a lunar regolith. The rover itself has 5 instruments. It's a neutron spectrometer mounted in front to look for hotspots where you have a high hydrogen concentration or water. You have a drill subsystem. Sitting right over here. Near infrared spectrometer is looking at cuttings generated by the drill. Oxygen and volatile extraction node, or oven for short, is taking the cuttings and essentially volatilizing them, getting volatiles out, and these volatiles flow into Lunar Advanced Volatiles Analysis Subsystem, which is essentially a GCMS. This presentation is going to focus on a drilling subsystem. We call it a 1-meter drill. For over 10 years, we've been developing a drill, not for the moon, but for Mars, for Chris Zacny's icebreaker mission. And the purpose of the drill was essentially to capture icy samples from at least 1 meter depth below the surface. The drill spent many weeks in Antarctica, Arctic, Greenland, in vacuum chambers. So it was a pretty high TRL. Just recently, we have presented a pretty, great possibility of flying to the moon on board of a resource prospecting mission. And essentially, our goal was to turn a Martian drill into the lunar drill. From some perspective, that's easy because on Mars, we'll have to sterilize the drill. That's a dry heat microbial reduction, 125 degrees cooking for 35 hours. That's actually pretty tough to do. All the mechanical systems have to withstand this kind of temperatures. You have to deal with perchlorates, sticky samples, and things like that. So that's easy. But if you go to the moon, you have to deal with very high temperatures and very low temperatures. So you have these extremes. You have to work with hard vacuum. And from a volatiles perspective, you have to watch out for volatile losses. If you warm up volatiles above certain temperature, they're going to be gone in no time. And this is something that we don't see under Martian conditions. Initially, what we did is look at 4 different drilling options. First one is sonic, so it's sort of like a toothbrush, but much bigger, vibrating toothbrush. Then ultrasonic, percussive, and rotary. For many reasons, we removed sonic, ultrasonic, and percussive was left behind. It's actually a really good approach for penetrating very hard formations. Rotary, on the other hand, was very good for penetrating very soft formations. So we pulled percussion and rotation, and we turned it into a rotary percussive drill, but we decoupled rotation from percussion. So now we had 3 modes, percussive, rotary, and rotary percussive, depending on the sample that we have to capture. Initially, our drill was 40 kilograms. That's this one mounted right in front, deployed from a robotic arm. And then the drill went into a slimming diet and dropped from 40 kgs all the way down to 10 kgs. And this is the drill that has been thoroughly tested on a rover, and it's being actually tested right now at Johnson Space Center. We also looked at the sampling traits. How do you get a sample from a subsurface to the instruments? And I usually like to show this plot. It's a complexity plotted as a function of science payoff. Complexity, this is what engineers care about, whereas science payoff, this is what scientists care about. And this fence right over here this is where we meet, and there is a fight going on. Scientists, obviously, they want to find themselves here. whereas engineers will want to stay somewhere down there because it's easier. From a science standpoint and the complexity, the easiest thing is to put an embedded sensor inside a drill. It could be as simple as a thermocouple and even a neutron spectrometer. So this is a neutron spec we developed with Rick Altek here at Ames. For this system to work, you have to go below the surface. Your job is done. You can look at epithermal and thermal neutrons. On another extreme, you have a coring system. So here you need some kind of a drill that goes down, breaks the core, captures the core, pulls it out, dispenses it into some kind of receptacle. Then ideally you want to crush the core and present it to the instruments. So there are so many very difficult steps, and each of these steps is essentially a miracle. That's why from complexity standpoint it's very high, but science payoff is very high as well because you get a core which you can analyze. As a note, the Mars MSL Curiosity initially back in 2006, 2007, it was supposed to be a coring system, coring drill, but it was found that there's just way too many mechanisms, actuators required to do this job, and the Curiosity has a powder acquisition drill. For Lunar Resource Prospector, we decided to be somewhere in the middle. We're essentially capturing the cuttings, which are augered to the surface, and we send them to the instruments. And we developed this so-called bite sampling approach. In a bite sampling system, the auger has a very shallow flutes and very deep flutes. This section is called the bite section and is designed to capture the sample and preserve it. The section above it has been designed to efficiently move cuttings to the surface and prevent binding. So in a concept of operation, you drill down 10 centimeters, you pull out, you brush over the sample through this passive brush into a container, you go back for another 10 centimeters. And this approach, taking bites every 10 centimeters, has actually quite a few advantages. Your stratigraphy is preserved in these 10 centimeter bites. You reduce a risk. I call it a graceful failure, because if you get stuck at 60 centimeters, you already have samples, 5 samples from above it. You also give a time for instrument to analyze the sample while the drill itself is above the ground, which is in a safe position. And you also give a lot of time for the drill and also subsurface to cool off. For the drill itself, the operation would look something like this. You drill down through the bites, and eventually you get to the ice-bearing material. You capture this, you look through with a near-infrared spectrometer or NERVAS, and you find, hey, there is some ice over here, and the sample that's captured right over there can then be sent to the oven and the lava for analysis. This movie shows prototype drill that has been developed for Mars mission. It's sort of like a resource prospector mission. In this case, we have a fully autonomous drill, 10-kilogram drill system that goes down to the ground, then drills up to, I believe, 80 centimeters. That's a requirement for this particular drill. Captures the sample on the flutes. All the stuff that you see is done autonomously. Pulls it out of the ground. And in this particular case, we had to drop the sample off into the carousel with a bunch of cups. So you can see sample being dropped into the cup, and then this cup presents the sample to a Raman spectrometer and imager. For the resource prospector, the idea was to show that we can capture icy soil and we can preserve volatiles before the sample is delivered to the oven. The drill was taken to the NASA Glen, was put inside a lunar vacuum chamber. So that's our drill sitting inside the bottom half of the vacuum chamber. You can see the rim over here. And the goal was to capture the sample, actually 6 samples, and deliver them to one of those 6 crucibles. We used a lunar simulant called NULHT-3M, which was frozen to around minus 60 degrees centigrade. It was compacted to 1.5 gram per cc. This is how the system was assembled. You can see the sample being inserted into the bottom half of the vacuum chamber. Then you put the cooling coils. This is the drill on the XY stage, so you can move up back and forth. So you can drill a couple of holes. This drill goes on top. Then you put a cooling shroud, and then you put the outer shroud for the top lid for actually pulling vacuum sealed. Since the entire chamber was closed off, we have 4 cameras inside looking at some of these 6 crucibles. So they're actually shown right over here. That's this picture looking through a camera. We are looking down at the salt bin, and another camera looking from other side. This movie shows the drill deployment. So the drill goes through a seed routine, goes down and tries to find the surface. There is a feedback control system that tells you exactly when you touch the soil. Then once you touch it, you go through a drill routine. You essentially go to a predetermined depth and you capture the sample. Then you go to a dump routine. Here the drill moves over, and you can see actually sample being dropped off into one of the 6 crucibles. And once this operation is done, the goal was to essentially hermetically seal one of the crucibles. So this is sealed, and this operation is done. We go back to the sample. We capture another sample from predetermined depth. We dump it to the next crucible, and we do it 6 times. So this is a picture after we broke the chamber, 6 holes, and this is one of the crucibles with the sample inside it. This is quite interesting graph. What it shows is percent of water loss on this axis. Here's a sublimation rate on a z-axis, and here's ambient temperature inside the vacuum chamber. And this line is essentially a theoretical sublimation curve. It essentially shows that at higher temperature, ice is going to sublime much faster. At lower temperature, is going to sublime much slower. Our samples, which was delivered to crucibles at different temperature, essentially almost fit this theoretical curve, which means volatile loss is a function of temperature inside the vacuum chamber. And just as a note, we've done a lot of testing inside the Mars chambers. And maybe some of you remember the pictures from a PNX landing site where we exposed ice to the atmosphere. Next sol, the ice was still present. Second day, you could see ice essentially slowly subliming away. So Mars is pretty graceful in this regard because you have some time to capture the ice. On the moon, I blinked and the ice was gone. Okay. In this vacuum chamber, we watched through the cameras. We watched the surface. Initially, there was a frost. Once we start pulling a vacuum, we got to the certain vacuum level, and the ice was gone in no time. So the biggest, in my opinion, the biggest issue about capturing volatiles on the surface of the moon is essentially do it at very low temperature and move them as fast as you can. And some of the scribbles, this is actually drilling data. On average, it took us 10 minutes to capture 10 centimeter bind. The power was around 20 watts with force of around 30 newtons. So it's pretty low. Currently, the drill has been integrated at NASA Johnson Space Center. That's the drill drilling into JAC-1A simulant. That's a rover itself with wheels, and we are conducting various operations. And next month, the rover with the drill go outside and is going to perform end-to-end operations. Here, what we see is the drill being slowly preloaded against the sample. And on this next movie, here we see the drill actually capturing the sample and right now dumping the sample onto the ground. You can imagine that there is going to be a crucible at the end to capture these icy samples. So this was essentially a demonstration to show we can do it given the power of the rover itself and the energy supplied from the batteries. I'd like to acknowledge NASA ASTIP, ASTID, PDIP, and SBIR, as well as Exploration AED division. Thank you very much.